So in this video, I'm just basically going to explain to you how you find the nth derivative of some function using power series. It can basically be a Maclaurin series or a Taylor series. And so remember, let's say maybe you have this function f of x is basically equals to 1 over x minus 4. Yeah, so let's say you have this function right here. And so let's say maybe we want to find the 100 derivative of this at 0. So how do we find that? How do we find the 100 derivative of that at 0? Notice that here, basically what we can do is like, we can basically find the nth derivative of that function. I'm just going to easily show you how you do it without power series. If it's doable without a power series, then yeah. But I'm going to then, I will then show you how you do it using a power series. And so how do you find the 100 derivative of this? Notice here that basically you're just going to have f prime of x is just basically going to be minus 1 over x minus 4 all squared. And then if you take the derivative of that again, then you're just basically going to have like the derivative of the denominator, there's just going to be 2. The derivative of the inside part, it's 1. So you're just going to have 2 into x minus 4 divided by x minus 4 raised to the 4th. So of it, which if you simplify, you're just basically going to obtain something like this, x minus 4 to the power of 3. Take that derivative again, and basically you're just going to have f triple prime being something like derivative of this is just going to be 3 into that. So you're just going to have negative into 6 divided by x minus 4 to the power of 4. So basically you have something like this. Take the derivative again, then you can have the 4th derivative of that. And so basically you're just going to have 6 by 4. And so basically notice here that this is just 1, and this is the same as just saying 2 by 1. And here 6 is the same as you're just saying 1 by 2 by 3, or 3 by 2 by 1. This is basically the same as you just have negative of that into x minus 4 raised to the 4th. And so basically you can already see the pattern there. So we can basically just say the nth derivative. Notice that here this is just factorial. It can just be denoted by a factorial. And so that means that the nth derivative of that will just be n factorial. And notice that here, basically here you just swap the signs. For the first derivative you have a negative, and for the second derivative you have a positive. So every even derivative will just basically be positive. So we can have minus 1 to the n. If n is 1, you're just going to basically have negative, and if n is 2, you're going to have a positive right there. And notice that here this is just the same power as basically just going to be the power plus 1. This is the third derivative if you have power 4. The second derivative you have power 3. The first derivative you have power 2. So then that means that you're just going to basically have x minus 4 to the power of n plus 1. And so that basically means that the 100 derivative at 0 of that, then you just basically plug n as 100, and minus 1 to the 100 is going to be just positive 1, right? And then you're just going to basically have a 100 factorial divided by, now you're substituting x as 0, and so you're just going to have 101 because it's 100 plus 1. And so that means the 100 derivative at 0 of that function is just going to basically be 100 factorial over minus 4 raised to the 101. So that's just going to be the 100 derivative of this function at 0. So now what if you don't want to do it like this, you want to do it using a Taylor series. Specifically, it's going to be a Maclaurin series for this one. So remember that whenever you have like a function and you're basically taking the n derivative of that, at that point, you're just going to need the series should be centered at that point. That's because if it's centered at that point, then that means that all the other terms will just basically go to 0, and I'll just show you in a moment. Okay, so that means that we need a Maclaurin series of this. What's the Maclaurin series of 1 over x minus 4? So notice that here we can just basically think of this as like a geometric series to infinity. If we think of this as a geometric series raised to infinity, then we can basically see a few things. Remember, the sum to infinity of a geometric series is basically written as like a over 1 minus r. So basically, if we see something like this, that means we can do some conversions right there. So that means that we need to identify a and r. And remember, the sum to infinity of that, we can basically just denote it as when n goes from, you basically need to start from 0, or you can start from 1. Doesn't actually really matter for this case. But so let's start from, let's just basically start from 1 raised to, okay, if we need the Maclaurin series, then let's start from 0. Okay, so let's say we start from 0 to infinity. So then that basically just means that we are supposed to have just a multiplied by r to the power of n. If we started from 1, we'll have n minus 1, right? This is the same geometric series that you know. I just tweaked a little bit right there. Don't let it confuse you. Okay, so now, remember what I said? I said if you want to put 1 here, then you'll have n minus 1 right there. So the key size idea is just that my first term should be a in both cases, okay? So don't be confused. So now you have f of x, let me just write that down. You have f of x as 1 over x minus 4. And so I can rewrite that as negative into 1 over 4 minus x. And so then when I have this, remember I basically need to have a 1. You have to relate that to the sum to infinity formula right there. And so basically what I can do is like I can then divide both numerator and denominator by 4, or I can just say 4 into 1 minus x over 4. That's basically what I have. And remember, I still have the negative on the outside right there. And so basically I can just take this and say I have a negative and divide both numerator and denominator by 4. So that means I just basically have 1 over 4 into 1 minus x over 4. So then I can obtain like the Maclaurin series of that. Notice that here I can just basically say I have something like this, minus 1 over 4 into, divided by 1 minus x over 4. So then I can rewrite this as a power series. And so Maclaurin series of that. And so that's just basically going to just simplify to something like this. The summation from n equals 0 to infinity of minus 1 over 4 multiplied by r in this case is just going to be x over 4. So I basically have x over 4, and then I can raise it to the power of n. So that's basically something that I have right there. And so keep in mind that this formula here is just basically valid for the absolute value of x over 4 being less than 1. So that's another thing to just keep in mind right there. And so now that we have this is basically f of x, right? Written in series form. And so when we have this, then what we need is to find like the derivative of that. So specifically the 100th derivative of that. And notice that here, if you basically expand this, you basically realize that you're just going to have minus 1 over 4. And then you basically have your second term. Just keep in mind every term is just going to be affected by this negative right there. So you plug in x as 1, so you're basically going to have minus x over 16, and minus again you're just going to have x squared over 16 by 4. Let me just write 4 cubed right there, and you're just basically going to have minus x cubed over 4 to the 4th, and that pattern is just basically going to proceed like that. And now notice something here. If you take the first derivative and you evaluate it at 0, that's just going to be minus 1 over 16. And why is that? Because now if you take the first derivative of that, you're just basically going to have minus 1 over 16 minus 2x over 4 cubed minus 3x squared over 4 to the 4th minus that, and the other derivative. And if you plug in 0, notice something. If you plug in 0 here, notice that every other term will go to 0 except the first one, right? You see that? Except the first one. So now we can basically think of it like this. Whenever we take the derivative, notice that here, the nth derivative of that, let me just say it like this. You see here I have x to the power of 2. I take the first derivative and I have 2x. If I take the second derivative of the very same term, then that means I'll just have the derivative of 2x, which I have 2. Here I have x to the power of 3. Take the derivative of that, you have 3x squared. Take the other derivative, then you have 6x. So basically what I'm saying, the key size idea is that here, if I have x to the n, and I take the nth derivative of that, the nth, I'm just going to assume n is an integer, but it is an integer in this case, so right here, it's nothing new. If I take the nth derivative of that, I'll remain with a constant. That's what I'm saying. If you take the nth derivative of x to the power of n, you'll remain with the nth derivative, right? You'll remain with the nth derivative. And notice here that every time we derive x squared, the first derivative is 2x and the second derivative is 2. It's a constant, so what I'm basically saying makes sense, right? So if you have x to the cube, notice that you have 3, and then that 3 is going to be multiplied by 2, and then you'll have 6x, and that 6 is going to be multiplied by 1, and that gives us 6. And 6 is the same as 3 factorial. Notice that here you basically have n factorial. You see that x squared, you have 2x, and then you have 2, which is the same as just saying 2 factorial. You see the pattern here. And so that means that I expect to get n factorial. And then what happens there? And that's just basically what we have. If you take, it doesn't matter. I can give you an example here. You have x squared. Take the second derivative of that. You're just going to have the first derivative is 2x and the second derivative is 2. 2 is the same as 2 factorial. You see that? You have x cubed, and then you take the derivative of that, you have 3x squared, and you take the other derivative of that, you have 6x. Take the third derivative down, you just basically have 6. 6 is the same as 3 factorial. You see that? That's one of the things that you need to analyze in this whole thing. And now notice something. Let's go back here and ask ourselves what basically happened. You know that here, if you take the n plus 1 derivative, if you say dn plus 1 over dx to the n plus 1 of x to the n, that's just basically going to be 0, because the derivative, the nth derivative is a constant. The derivative of a constant will just basically be 0. So that means every other term which is less than that will basically be 0. So that means if you take the 10th derivative of x to the power of 9, you're supposed to get 0. But that's basically the same as just saying it doesn't really matter as long as like the derivative, the degree of the derivative is higher than the power, then that answer is just going to be 0. So that means that if we are taking the 100th derivative of this, that means every power less than 100 will basically be 0. The derivative of that will be 0, right? That's what I'm saying. That's what this statement here is saying. Don't get lost, right? And so what happens when we actually reach x to the power of 100 here? If we take the 100 derivative, we expect that the first number that appears there should be the 100th power of that, right? So that means that we only need to just consider x to the power. We just only need to consider where x is raised to 100. If I have a 100 derivative, I only have to consider where x will be raised to 100. So if they wanted the 102 derivative of the 55th derivative, then you'll consider where x was to the power of 55. And so what you do in this case is you can basically rewrite this formula here. Isolate x to the power of n. That way it's easier to get the coefficient. So I'm just basically going to have minus, I'm just going to rewrite that series there from 0 to infinity and say minus 1 over 4. And then I basically have 1 over 4 raised to the n and x to the n. It's when I rewrite that. And since I'm looking for the 100 derivative, I consider where x to the power of n will be 100. X to the power of n will be x to the power of 100 if n is 100. So now you consider n being 100. And this is the coefficient, right, that we have right there. So you multiply the coefficient by n factorial. You do that for every derivative that you have, 55th derivative or stuff like that. You consider where that power is to that degree of the derivative. And the rest of them, that will just basically be 0. And so that means that the 100 derivative at 0 of that will just basically be the coefficient there, 1 over 4, minus 1 over 4 by 1 over 4 raised to the 100, because x to the power of n is 100 if n is 100, right? That makes sense, right? And so then you multiply by n factorial. That's that. And so in this case, you're just going to have 100 factorial. And then if you look at it right there, if you do your further simplifications, this will be the same answer that we have right here. It shouldn't be scary because you have 1 over 4. You basically have something like this, minus 1 over 4 by 1 over 4 to the 100, because 1 to the 100 is the same as 1. And so you multiply that by 100 factorial. And then notice something here that you have 4 and 4 to the power of 100. That will just basically be 4 to the power of 101. So that's basically that. Let me repeat what I said. You have a power series that you have will basically be something like this, right? So let's say that you have f of x written as something like this. It's going to be some coefficient multiplied by x to the power of n, right? So if you're looking for the nth derivative at 0, the nth derivative at 0, then that function here, fn at 0, will basically be that coefficient evaluated at n. So you'll just basically have cn, multiply that by n factorial. That's basically what we have. And it shouldn't really be scary. If you have a Maclaurin series, it will be at a, right? So suppose that maybe you have that function, something like this. Let's say g at x is given by this series right here. So let's say it's c to the n into x minus 2 to the power of n minus 2. If you have something like this, be careful. Be careful. If your series has tweaked the value of n here, if you're looking for 100 derivative in this example, 100 derivative, let me just write it like this, g prime at 100 at 2, evaluated at 2. This is what you're going to have. Where will x be raised to 100 here? X will be raised to 100 if n minus 2 is 100. If n minus 2 is 100, if n minus 2 is 100, then that basically says that n should be equals to 102. So that means that g at 100 evaluated at 2 will just basically be equals to c of 102. Yeah, that's when we tweak a little bit. I'm just gonna give you like a proper example, not a more abstract thing, because people don't like more abstract things. Yeah, it's better to just give like an idealistic example, just one example, and that should be enough. And so you'll have c to the power 102 multiplied by obviously it's just gonna be n factorial. But remember, we tweaked a little bit, so that means that we expect n minus 2 factorial there. So that's basically gonna be that. So basically, it even says itself that 100 derivative. So that means that here it should just have 100 factorial. This will just be 100 factorial. Okay, let me give you like an example of what we have. So suppose they give you g at x equals, let's say, is the summation from where n equals to 0 to infinity of, let's say, 1 over n plus 2 factorial multiplied by x minus 2 factorial. Maybe just, let's say, 3n minus 3. Okay, so let's say they give you this now. Find g at 100 of evaluated at 2, obviously, because we want other derivatives to be 0 at 2. So that's basically the idea there. So now, here, how do we get this? Remember what I said. You consider where x will just have a power of 100 right there. So that means that consider where, basically here you can just call this one Cn, right? Consider where 3n minus 3 will be equals to 100. So that basically just means that, technically just going to give us fractions. So I just say minus 2 instead. Will that work? And we have 1 or 2. That's going to work. I don't want n to be fractions. Okay, so consider this now. How do we find the 100 derivative of that? You consider where 3n minus 2 will be 100. Because if that's 100, then that means we'll have x to the power of 100 there. So that basically implies that 3n will be equals to 102. And 102 is the same as you just say 90 plus 12. And if you have 90 plus 12, how many times does 3 go into 90? It goes 30 times, and it goes 4 times in that. So you're just basically going to have 34. So you consider n as 34 in that case. And so from then it just basically be easy. So remember I said let this thing be Cn. Whatever that doesn't contain x, let it be Cn. So I have 1 over n plus 2 factorial. That's that. And so that basically means that I have to find c at 34. C at 34 will just basically be 1 over 34 plus 2 factorial. So we'll basically have 1 over 36 factorial. That's that. I have that. So what do you have to multiply it with? 100 factorial. Yeah, right? So that's that. So yeah, it's that easy. So that means that g, the 100 derivative at 2 of that function is just going to be c34 multiplied by 100 factorial. And so basically, you're just going to have what? C34, which is 1 over 36 factorial, multiplied by 100 factorial. So basically, you have 100 factorial divided by 36 factorial. That would just be that. Yeah, but it's basically easy. Another way to look at it is to just analyze. So let's say suppose n is 34. Then what term exists in that series? That's raised to 100. There exists 1 over 36 factorial multiplied by x minus 2 raised to 100, right? But then you can basically make sense of the formula that I told you right here and say, okay, I know that if I take the n derivative, I'm supposed to have n factorial. But then you treat this as a constant whenever... Then you treat this as a constant. And remember, whenever you derive, you can basically take a constant outside, derive that, and then later multiply with that constant. That's basically what I'm doing right here. I have C34, I ignore it, and then I consider where this will be to the power of 100. So similarly, try to find G55, the 55th derivative at 2 of this function. You want to know the answer? So you consider where 3n... will it be possible for 55 though? And 3n minus 2, that would be 57. Yeah, it's possible. G55. Cool. So for 55th derivative to find G55 of that function evaluated at 2, that's basically going to be equal. You consider where 3n minus 2 is equals to 55. And then consider 2 that side, then you have 3n equals 57. So divide both sides by 3, that's going to be 19, right? You basically have 19. So you have 19 plus 2, which is just going to be 21. So that means that you have 55 factorial divided by this. It's basically multiplied by this one, but this one is just 1 over that. So I'm just going to say 1 over n minus n plus 2. So that's 19 plus 2. That's going to be 21. And then you just basically have 21 factorial. And then that's how you just analyze this. Basically, it's just that. Okay, so yeah, that's it for this video. Just hope you can find the n derivative of any function. as long as it's expressed as a Taylor or a Maclaurin series, then you can find it. And if it's not expressing that, so you can first find the series expansion, the series representation of that function, and then you basically do the same process. Okay, thanks for watching.